This Part 5C explains how the control strategy was implemented. There are 3 circuit boards mounted in the tender. Power amplifier A, which drives the 3 tender motors, power amplifier B, which drives the locomotor, and the control board, which I will describe first. The control board uses operational amplifiers, op-amps for short. I don't intend to go into the theory of op-amps. There are plenty of videos on YouTube which already do this. However, I will explain the purpose of each op-amp stage. At the top of the board are 2 DC to DC converters, powered by the lead-acid battery or batteries. The first converter provides stabilized plus and minus 15 volt supplies for the op-amps and their associated circuitry. The second converter provides a stabilized plus 5 volt supply for an incremental encoder used in the speed and distance measurements and some other devices. These Traco converters turn up on eBay from time to time and are an excellent buy since they will operate efficiently with an input voltage that varies from 9 volts up to 36 volts, and they have a very good specification. At this point I will start explaining the circuit diagram. Integrated circuit A is a dual op-amp in an 8-pin package. The 2 op-amps are organized as a ramping circuit, sometimes referred to as a variable slew rate circuit. We touched on ramping before, but now we'll consider it in more detail. There are 2 reasons to avoid abrupt changes of the demand voltage at the input of a motor power amplifier: damage to the motor, either mechanical or magnetic, or damage or excessive wear of the gearing. A careful driver can avoid these by gentle operation of the demand pot, but it's safer to use electronic intervention to limit the input slew rate. The basic way to limit the rate of rise or fall of a voltage is to make use of the charging of a capacitor. In the circuit shown, the capacitor initially has 0 charge, so the voltage across it, Vc, is 0. When a step of voltage Vs arrives, since Vc is initially 0, Vr equals Vs, so the capacitor C charges at the current given by Vs over R. However, as the capacitor charges, Vc increases, so Vr reduces. Therefore the charging current reduces. The net result is that Vc increases as an exponential, as shown in this graph. It's like walking towards a destination, and the nearer you get, the slower you walk. If, on the other hand, we keep the charging current constant until the capacitor voltage equals the step voltage, we achieve a linear ramp. This diagram shows a range of possibilities. The first ramp starts at the same slope as the exponential. We can choose a slower initial slope, but arrive at the demanded value faster than the exponential, so a ramp circuit is a better choice. This diagram shows 3 circuits. The first circuit uses a simple RC arrangement, followed by a unity gain buffer to present the output at low impedance. The second circuit provides a unity gain stage with linear equal rise and fall times set by resistor R. The third circuit allows the rise and fall times to be set individually by R1 and R2. The 100K resistors bring the demand to 0 should the demand pot fail or become disconnected. Originally the control card had circuit 1, but I later modified it to circuit 3. These clips show test results. The oscilloscope is an eBay Chinese DSO 138, which, although it only cost £15, is very versatile. This photo shows the third circuit, now built into the control card, in action. The demand pot was initially abruptly turned from minimum to maximum. Then, after a short delay, it was stepped down with pauses. The ramp up is set slower than the ramp down. Op-amp B buffers the output of the tender Hall effect current sensor. The tender power amplifier output cable goes through a hole in the center of the sensor. The unit then detects the magnetic field from the cable and provides an isolated small current output scaled so that 50 amps motor current would give an output current of 25 milliamps. The control circuit passes this 25 milliamp current through a 200 ohm resistor to provide a full scale of 5 volts. An input filter is provided to reduce noise. The output of the op-amp feeds a scaled meter in a handheld controller. but it can also feed any other monitoring device. The diode minimises a reverse current indication to avoid damage to the handheld meter. We can see its operation here with a spare sensor. The maximum test circuit current that I have available is 5 amps. I've therefore fed this test circuit through the sensor 5 times, so the combination simulates 25 amps. When monitoring the tender current, the hand controller meter is scaled for 50 amps, full scale, so we can see it here showing half scale. Op-amp C provides a similar purpose for the loco current sensor. However, it is scaled for 20 amps full scale, since the maximum current is planned to be in the order of 10 amps. Using the spare sensor with 5 turns, we can see that on the hand controller, 4 amps gives full scale and 2 amps gives half scale, as intended. Op-amp E buffers the output of the loco maximum current set point potentiometer. Op-amp D uses a configuration known as a summer. It has 2 inputs, the loco current monitor from op-amp C and the maximum current set point from op-amp E. These 2 signals are of opposite polarity, so if they are equal numerically, the sum would be 0 and the output of op-amp D would be 0. Provided the monitor current is well below the set point, the output of op-amp D will, because of its inverting gain, be near the positive limit, and diode D2 will be reverse biased. In this state, the current limit is inactive. As the measured current approaches the set point value, the output of op-amp D will drop until the diode D2 starts to become forward biased and holds back the positive current drive in the Uni 8. The sharpness of this limit can be set via op-amp D gain pot. The gain must not be set so high that instability occurs. Diode D1 avoids unnecessary excursion in the negative direction. The set point has been adjusted so that the current limited starts progressively from 9 amps. Op-amps F and G are not part of the control system and just scale and offset the battery voltage measurements to cover the ranges 11 to 13 volts or 22 to 26 volts for the handheld controller. This allows 3 possible 12-volt battery configurations to be monitored: a single battery, 2 in parallel for more endurance, or 2 in series for higher speed. This photo shows the meter on the hand controller indicating half scale, that is 12 volts. We now come to the power amplifiers that drive the motors. When discussing voltage control, we assumed a smooth DC voltage. If we used an analog amplifier to provide this, it would be incredibly inefficient, particularly at high current, low speed. What is required is a pulse width modulated amplifier, or PWM. I don't intend to explain PWM, there are plenty of videos on YouTube that do that. However, I will go into some of the details of the amplifiers used. Initially I planned to design my own amplifiers. I've had some experience in designing such devices. Then, on eBay I noticed 3 PW amplifiers type Uni 8, made by the company 4QD. They're not a current model, but I've used this amplifier professionally and had a full circuit diagram. So the fact that they were listed as faulty was not a problem, and they went for a song. It turned out that someone had interfered with the current limits, but it took only a few minutes to correct. The amplifiers were 24-volt versions, and I wanted to run initially on 12 volts. This was no problem, except that there was a 24-volt relay at the supply input to protect against supply reversal. My plan was to fit battery leads that were too short for reversal, so I simply shorted the relay contacts and cut through the relay coil tracks. I didn't bother to remove the relays. The Uni 8 has a current limit that uses the voltage drop across its lower MOSFETs in the on state as a measure of motor current. This is okay at higher currents and has some advantages. For instance, if the MOSFETs start to get too hot, the voltage drop is greater and the current limit automatically comes in at a lower current. This approach was okay for the tender, and I set it initially to 30 amps, which is fine for my garden railway. It could always be raised later on test. However, it didn't work well at currents in the region of 10 amps, so for the loco I set it to 20 amps but used the external circuit I described to cut in earlier, This is where having the circuit diagram helped. These clips use an eBay PWM generator set to 20 kHz, the same frequency as the Uni 8. Three different duty cycles are shown: 40%, 60%, 90%. They demonstrate that although the voltage is PWM, the current is significantly smoothed by the inductance of the motor, so our voltage control principles still apply. For this test, the current is monitored by observing the voltage drop across a 0.1 ohm series resistance. Unfortunately, this low-level signal suffers from some 50 Hz pickup. Since the measurements are referenced to the positive supply, the current would be shown upside down. But the oscilloscope channel 2 allows inversion. Channel 1 cannot be inverted, so the voltage signal is shown upside down. The oscilloscope is an Iwatsu SS5702 that I bought on eBay in 2013 for £39. It was built in Japan, and apart from needing the odd application of contact cleaner on the switch contacts, has proved very reliable. The Uni 8 does have internal ramping circuitry, but I wanted both amplifiers to ramp synchronously, so I set these to fast and relied on my external circuit, which is common to both. Since the Uni 8 is unidirectional, I used automotive relays to provide reverse. These are arranged to operate in parallel for 12 volts or series parallel for 24 volts, as selected by a switch on the right of them. They are mounted above the tender motor bus bars. The train reversing switch is on the hand controller and should only be operated at rest. It's a locking type to avoid inadvertent operation. This photo shows the control panel situated below the rear tender plate. There's a master isolating switch, the actuator of which can be removed for safety, and 3 fuses, plus a number of switches and LEDs that can be used for testing purposes. The motor wiring goes through circuit breakers, which could be operated at the back of the tender in an emergency. This circuit shows the interconnections. Between the power amplifiers and the relays, one motor wire of each drive goes to the Hall effect current sensor. The main battery fuse is next to the battery connector. Part 5D will explain the sound system, plus the speed and distance readout.